Get to the math part. So since maybe we can do a better job investigating, complex limits by finding too low and too high estimates. Why do our limited properties not work on this one? The limit as x approaches 0 of x squared times sine of 1 over x. Why is that a problem? What's wrong with that limit? What's our strategy when we evaluate limits? First one we try. Substitution. What happens when I throw a 0 in there for 1 over x? It's undefined, right? So it doesn't work because the sine of 1 over x is undefined. Okay, so let's just break it down a little bit. Let's take it away. Let's don't do 1 over x. Let's just talk about sine of x. Okay, what values does sine of x always rotate between? If you think about the graph of the sine, it's your roller coaster. What does it always go between? 1 and -1. Okay, so what about sine of 1 over x? Does that change? If I put it on in the calculator, does it change what it rotates between? It doesn't, okay? It stays between -1 and 1. So then it's like, okay, let's apply a transformation, okay? So they've applied a transformation. They put a 3 in the front, so an amplitude shift in there. If we looked at our calculator, what does 3 sine of 1 over x rotate between? -3 and +3, okay? What about 1/2 sine of 1 over x? What does it rotate between? -1/2 and 1/2. Okay? So if that's the case, what can we say that k sine of x rotates between? K and -k. It's following the same pattern. If I put an amplitude shift out there, all right, we change the amplitude, it changes the range. Okay? Okay, so now they want me to extend that same concept, all right? So using what we see here, all right, what would x squared sine of 1 over x be sandwiched between? -x squared and x squared. Okay, it would be sandwiched between -x squared and x squared. So the opposite of x squared and x squared follows that same pattern. Okay, which is kind of nice. We've got this nice little pattern thing going on. So now let's talk about limits. Okay, so our lower function, so we want to know what is the limit as x approaches 0 of the opposite of x squared. All right, so let's put that in there. Okay, direct substitution, what would I get? I'd get 0. All right. If I do the limit as x approaches 0 of positive x squared, so of our upper bound, all right, what do we get? 0. Okay. So if that's the case, all right, if those two limits both equal 0, any guesses as to what that whole limit's going to equal? 0. Okay, it is the limit as x approaches 0 of x squared sine of 1 over x is indeed 0. And the reason that's true is because that function is sandwiched between the other two. Okay, so this one must be 0. This is the squeeze theorem. Now, you've not thought a lot about what that function looks like if we graph it. Okay, this is what we refer to as a damped trig function. Okay, which basically means we take these lower bounds, all right, and we graph them, bless you. So -x squared would look like this, x squared would look like this. So there's our two upper bounds and our lower bounds. So y equals the opposite of x squared, y equals x squared. And what we do is we sandwich sine of x between those two functions. So sine starts at 0, goes up, all right, gets our roller coaster, and that roller coaster is just going to grow and grow both ways. So it looks something like that. If you graph the whole function, that's exactly what it looks like. Okay, and so if we think about as x approaches 0 of that green part, it is indeed getting close to 0. Okay, that trig function is sandwiched, it's squeezed between those upper and lower bounds, right? And that is the squeeze theorem. It's really kind of powerful. It allows us to evaluate some limits that otherwise we wouldn't be able to do. Okay, so we squeeze it between those upper and lower bounds. So let's formalize it. I said we'd always do we do a lot of formal mathematics this year, and that's what we're going to do. Let's formalize the squeeze theorem. Now, people refer to squeeze theorem by lots of different things. I hear it called the sandwich theorem, all right, because it sandwiches between the other two functions. Some people call it squeeze play, all right. I've heard people call it the pinching function. It pinches it between the other two. And this one I don't get at all. They call it the fly swatter. I got nothing on that one. I have no idea where that comes from. All right. But when I was in training, they were giving us all these different versions of what people call it. And I'm like, I have never heard that in 25 years of my life. Okay. So anyway, here's the formal definition or the formal theorem. Okay. This is what it says, right? It has what we call conditions. And so that's what I'm going to start with. All right. These are the conditions. If f of x, g of x, and h of x. You need to write this down because one of the places you're going to lose points is in your justifications. All right, are continuous, and we've not talked about the formal definition of continuity yet, but you guys know what it means for something to be continuous. Functions on an interval. Okay, so on some interval containing this value a, okay? And g of x is less than or equal to f of x is less than or equal to h of x on that interval. Okay, so there are our, I can't spell. Those are our conditions. Okay, you've got to have 3 continuous functions, and a has to be on the interval that we're talking about, and then those functions are sequential. G is less than f is less than h. Okay, and then this is your conclusion. Then, if the limit as x approaches a of g of x is equal to some number L, which equals the limit as x approaches a of h of x, so those two things have the same limit, by the squeeze theorem, the limit as x approaches a of f of x is also equal to L. Okay, so if the limits of the two ends are equal, then the limit of the middle is the same thing. Okay, so let's take a look at a few. How would we justify? How would we evaluate a limit? Okay, fill that in. Yes.
Do they connect in the middle, or are they?
This one does because it would go all the way to 0. X squared would be 0. Negative x squared would be 0. Sine at 0 would be 0. Yeah. But sometimes they don't. Like if you think of cosine, cosine starts up, but it would be squeezed down to wherever the upper and lower bounds start. Okay, you're good, bud. Okay. Alrighty, so let's look at this one. We want to evaluate it using the squeeze theorem. When we first look at this function, all right, we notice that if I put in that 0, 1 over 0 would be undefined, okay? Good news, cosine and sine have the same boundaries, right? What does cosine oscillate between? 1 and -1. It's a trig function, right? That's what it oscillates between. So we can apply the same process that we did with the other one. So let's think about what would your lower bound be? It would be the opposite of x squared. What would your upper bound be? Okay, so it's always the opposite and the exact same of whatever's being multiplied by that trig function that's sitting there. Okay, so the two limits I need to evaluate are the limit as x approaches 0, 0 because that's what my original limit is doing, okay, of negative x squared. The limit as x approaches 0 of positive x squared. If those two things are equal, then that will be the value of the entire limit, okay? So what's the limit as x approaches 0 of negative x squared? It's 0, and of positive x squared, so the whole limit is 0. That's what the squeeze theorem allows us to do. All right. So now let's make it interesting. All right, I'm going to pull some from AP Classroom. All right, where you get to see all the words, all the crazy things they're going to ask you about. All right, and how they're going to ask these questions. All right, here we go. So the function f of x is equal to the cosine of 1 over x times the sine of x cubed minus 1 over x to the fourth. Now, I know nothing about that function, okay? Absolutely zero when I think about it. But it goes on to tell me that it's bounded below by g of x equal to negative square root of 1.11 minus x squared, and above by h of x equals this, all right, on the interval from -1 to 1. We want to know, is there enough information to determine the limit as x approaches 0 of that nasty function we know nothing about, okay? Now, my immediate response to that is, well, let me think about the conditions, okay? First thing it tells me is that f of x is bounded by g of x. So I think we've got here that f of x is less than or equal, nope, sorry, I wrote that the wrong way. It's bounded below, which is g of x, is less than or equal to the function I'm interested in is less than or equal to h. So that's the first condition, and that was met, okay? I'm taking the limit as x approaches 0. Does 0 fall in the interval that they gave me? Yes, okay, 0 falls between -1 and 1, so we're good, okay? So x approaches 0 falls in -1 to 1, okay? Those were our two conditions, right? Those were our two conditions. So now let's do the limit as x approaches 0 of g of x, which would be negative square root 1.11 minus x squared. And we'll do the limit as x approaches 0 of positive square root of 1.11 minus x squared. Okay. Okay, so let's evaluate. Okay, if I plug in 0 to the top, what am I going to get? It's going to be a weird answer. It's okay. We're not going to get a new decimal, right? If I plug 0 in and I square it, I get negative square root of 1.11. Okay, 0 squared. And then what would the bottom limit be? Square root of 1.11. Okay. Does the squeeze theorem work? No. Okay. I had the information that I need, but the squeeze theorem doesn't work. Why does it not work? Those two limits are not equal. And so this is what we would say, because the limit as x approaches 0 of g of x is not equal to the limit as x approaches 0 of h of x, the squeeze theorem does not apply. Yes. Can be. Can be free response. It can be multiple choice. It'll show up lots of different ways.
So we don't know like what the margins are going to be?
They're not prescribed like they are in pre-cal. Yep. I'll show you as many different examples and what the general trend is for those, but I can't guarantee what you'll see. Yep. That's what makes it harder. Yep. Okay. All right. Let's look at this next one. This next one's good, okay? Typically what you would see on this one is it would be in a multiple choice because it gives you it gives you option 1, option 2, option 3, and so it'd be like 1 and 2, 1 only, 1, 2, and 3. Like they love that in terms of the multiple choice, okay? So let's take a look at this next one and think about what we could do. Which ones actually work with the squeeze theorem? All right, so here it is. It says let f, g, and h be these functions. So f of x is x squared sine of x, g of x is e to the x over sine of x, and h of x is e to the sine x. All right, all where x is not equal to 0. All of the following inequalities are true on the interval from -1 to 1, where x is not equal to 0. Which of these inequalities can be used with the squeeze theorem to find the limit of the function as x approaches 0? So it's wanting you to figure out which one of these actually works, like for the squeeze theorem, right? So the first one talks about f, right? If I'm looking at f, it says f is squeezed between negative x squared and x squared, okay? And so what two limits would I need to check in order to know if the squeeze theorem was true? For just this first one. Well, what are they asking me to approach? 0. So we're going to start by doing the limit as x approaches 0 of the lower bound, limit as x approaches 0 of the upper bound. Okay, will I get the same value for those two? Yes. All right. So is the first one doable by the squeeze theorem? Yes. Okay. All right. Check the next two. All right. They give you what the boundaries are. That's what they're giving you, are those upper and lower bounds. All right, if we check that second one, limit as x approaches 0 of 1 over x, limit as x approaches 0 of x plus 1 over x squared. Okay? Does the squeeze theorem work for those? No, they're both undefined. Okay? They're both undefined. In order for it to work, it has to equal a real number. Okay? So those are both undefined, so number 2 is a no-go. Right? And then we're going to do the same thing for the last one. We're going to take the limit as x approaches 0 of 1/4 x squared plus e, and the limit as x approaches 0 of x squared plus e. Right. What would those limits equal? E. Okay. If I square 0, multiply it by 1/4, and add an e, I'm still going to get an e, so the squeeze theorem would work. It would only work for 1 and 2. This is one where you would probably see, I called you the wrong name. You would probably see as a multiple choice, because it would have like 1 only, 1, 2, and 3, 1 and 2, 1 and 3, those kind of things. All right, so that's kind of how they'll assess you with those. All right. Alrighty, so the next thing I want to do is show you 2 special trig limits that come about because of the squeeze theorem. You're going to want to add these to your reference page. They're limits. If we know them, we can use them, and then we don't have to prove. I'm going to do a little trig to prove the second one to you, but I'm not on the first one because it's just plain old squeeze theorem. All right, so I'll rewrite it for you here in a second. I think you'll see it. Okay. All right, if you picked up your calculator and you put in sine x over x, all right, and graphed it, all right, so once you put it in your calculator, sine x, the whole thing divided by x, and graph it. You can zoom trig it so you can see it better. Okay, so if we just look at that limit graphically, all right, as we approach 0 from the left and the right, what's it getting really close to? What's my limit as I approach 0 from both directions? What are we getting close to? 1, okay? And that's the value of that limit, right? Now, okay, cool. Do the same thing with the second one, all right? 1 minus cosine x over x. Tell me what it gets close to. So using our graph, if there's a limit we're not sure how to do analytically, we can always look at it graphically if it's calculator active. Okay, and what does that one get close to? 0. Okay, it gets close to 0. So those are 2 limits you definitely need to add to your reference page. We want to be able to use them, all right? And here's why. Here's a cool thing. This one also works if I do the sine of kx over kx. So as long as the number inside with sine matches the number outside with x, it still equals 1. Even cooler, the reciprocal is also true. Okay, and those limits are going to show up in things. So if I have, sine of 4x over 4x, it's still just 1. All right, or if I have the limit as x approaches 0 of 7.2x over sine of 7.2x, it's still equal to 1, okay, which is nice. That's a limit that's going to always hold true, okay? Now, I'm going to take a second and show you the algebra behind that second one, why it's true, okay? You will not have to prove this time and time again, but I want you to see it, all right, because it's not beyond the scope of what we can do, all right? But I refer to these as our special trig limits. Remember when we did radicals, we used a conjugate? Well, we can do that with this as well. What would be the conjugate of 1 minus cosine x? What do you think is the conjugate of 1 minus cosine x? Yep, 1 plus cosine x. Okay, so I'm going to keep my limit notation with me because I'm not ready to quit just yet. If I distribute on that top, that's going to give me 1 minus cosine squared over x times 1 plus cosine. Okay. Now, probably going to need a trig identity of some kind, or maybe there's something we can do that would make this work. But let's just see. What's an identity? What is 1 minus cosine squared actually equal to? Sine squared. So this would be the limit as x approaches 0 of sine squared x over x times 1 plus cosine x. Okay. Now, I'm going to do a little arithmetic here. When we multiply, sine squared would be sine times sine. And when I multiply fractions, I multiply the denominators. So I can just kind of separate it like that. I didn't do anything illegal. Multiplying fractions looks that way. Sine times sine is sine squared. X times 1 plus cosine is x times 1 plus cosine. Because of that limit we have in the first one, all right, we know that the limit as x approaches 0 of sine x over x is 1. Okay, so we know this first piece is 1. For the second piece, we're just going to plug in 0. Okay, that's going to be sine at 0 over 1 plus the cosine at 0. Do a little evaluation. 1 times sine at 0 is 0. Cosine at 0 is 1. So that would be 1 times 0 over 2, which would just be 0. Right? So we're going to be able to use that limit as x approaches 0 of sine x over x to help us prove other things. Okay? Likewise with that 1 minus cosine over x, it's equal to 0. That's why. You're not going to have to do that all the time. I just wanted to show you, okay, that I wasn't just pulling this out of nowhere. Okay? So let's put those to use to see if it will help me to evaluate some other trig limits. Okay? To see if it will help me. All right, we ready? Here we go. Let's look at this first one. Okay. So let's see if we can use our new trig limits to help us simplify others. So the limit as x approaches 0 of tan x over x. Okay. Well, the first problem I see there's a tangent. Can I redefine tangent? Yes. Let's redefine tangent. So keep your limit. Sine x over cosine x divided by x. It still doesn't fix my limit because there's a 0 in the bottom. Okay. And this is something that I would caution you. A lot of you like to do your algebra and then just pick up your limit again at the end. You cannot do that. Okay. You have to keep your limit with you and you got to keep it organized. Some of y'all think kind of circular, which I think is really cool. I know that about you. So your math goes in a circle. Okay. They're not going to know that about you on the AP exam. All right. It needs to be very linear. So you need to start practicing that. Okay. Just practice. It's one of those things you'll get. All right. But we got to get there. Okay. So let's divide fractions. All right. If that's just x is x over 1. So this is the same thing as the limit as x approaches 0 of sine x over cosine x. Change it to multiply. X would become what? Yeah, reciprocal 1 over x. Okay. And this is where we want to use those properties, those arithmetic properties for fractions. Okay. I'm just going to switch the two denominators. Doesn't change anything because we know multiplication is commutative, all right? So I can change the order. So I have the limit as x approaches 0 of sine x over x times 1 over cosine, all right? So I just flipped the two denominators. I switched them, right? The reason I do that is because I know what that first limit is. The limit as x approaches 0 of sine x over x is 1, okay? In the second one, we're just going to plug in the 0, okay? So 1 over the cosine at 0. Well, what is the cosine at 0? It's just 1, and 1 times 1 is 1. Okay. So using our arithmetic properties, using a trig identity, not a hard one, all right, just the definition of tangent, and it will get me there. All right, the next two are probably two of my favorites because it's going to show you a lot of cool things that we get to do because of limit properties, and those will continue to show up when we do derivatives and integrals and all kinds of good stuff. Okay, so when I look at this first one, limit as x approaches 0 of sine 2x over x, it looks a lot like my limit, but there's a problem. What am I missing? In order for the limit to work, I need a 2 at the bottom, okay? And here's one of the cool things about math. As long as I multiply by a number equal to 1, it's legal, all right? So if I need to put a 2 here, where do I also need to put a 2 so that it's equal to 1? On the top, okay? And we're going to put it outside, okay? So 2 over 2. Now, I don't know if you remember, but when we talked about limit properties, we said if there's a coefficient inside, we can also just pull it outside, and it's the same thing. The only one I need to pull outside is the one from the numerator, okay? So I'm going to pull that 2 outside. That gives me the limit of sine 2x over 2x. So I did it on purpose so that I get my limit set up in the way that I needed it, okay? We can always multiply by 1. And it doesn't change anything. 2 over 2 is equal to 1, okay? I pull the top coefficient out. So now I have 2 times that limit, okay? As long as the number inside the sine function matches the number in the denominator, we're good. That limit's equal to 1. What is 2 times 1? It is 2. Okay, so we have to balance it. All right, only works if it's the limit as x approaches 0. Okay, only works there. Okay. And then let's look at this last one. All right, same kind of principle, except now they really jack things up. Okay, they put a 5 in the denominator, but what do I need to be there for it to work? The 3. So here's what I'm going to do before I start. Before I start, I'm going to go ahead and pull that 5 out. So it's on the bottom, so it's going to be 1/5 the limit as x approaches 0 of sine 3x over x. Okay, so the coefficient I don't need, I pulled out. Okay. Now, I need a 3, but I can't just throw a 3 down. I have to throw in a 1. Okay, so 3 on the inside. 3 in the denominator and 3 on the top, in the numerator. I don't need to leave the 3 in the numerator inside, so I'm going to pull it out. So now I have 3/5 the limit as x approaches 0 of sine 3x over 3x. What do we know that limit's equal to? 1. So I have 3/5 times 1, which is just 3/5. Okay? That's multiplying by a well-chosen 1, right? A well-chosen number 1. And we will do that kind of manipulation a lot, all right, where we'll fix coefficients to be what we need, okay? If you've got more than you need, pull it out in front, all right, and then put in what you need. It has to be a 1. Anything we add to has to multiply to 1, okay? Alrighty, so here's some practice for you. There's a worksheet back there, all right, 1.8. And those are just some AP Classroom type questions so you can see what they're going to look like, all right, AP level. And then out of your book, just some practice, page 70 to 72, all right, number 30, 32, 33, 67, 71, 73, 74, 75, okay? That's mainly just to help you look at some squeeze theorem questions and some of those kind of new trig limits, practice those, okay? Your wrap-up is active on Google Classroom, so do that for me. Callie, is yours started working yet, or is it still acting crazy? Okay, we'll see. We'll find out. Yeah.
My Google Classroom is still not active.
Yeah, you have to go to it through Safari.